very much for the invitation. I'm very sorry I'm not with you in Montreal today. So I hope you can hear me well. Okay. So so today I would like to present some work which appeared in arXiv last year. So about some folded version of quantum integrable models, and which is in part motivated by the deformations of W-algebras. So it's a joint work with Edward Frenkel and Nicolas Reshetykhin. So I will try to explain the ideas and the main results about this project. So there are two motivations, in fact. So I will start with informal explanation of the motivations, the double motivation. So the first one from this notion of deformed W-algebra. So it's attached to G, a simple Lie algebra, which might be simply laced or not simply laced. So there is a notion of deformed W-algebras, so which depend on two parameters, Q and T. So this is a version which was introduced by Frenkel and Reshetykhin, I think in '96. And so these algebra are motivated by various theory, in particular Q deformation of Virasoro algebras. And so they have some interesting limits. So there are two limits which were, in fact, intensively studied. So the first one is the T=1 limit. And then one gets an algebra which is closely related to the representation theory of an affine quantum groups. So it relates to the representation theory of UQG hat. So it is a quantum group attached to the untwisted affine Lie algebra corresponding to G. Then there is now the Q limit. So the limit when Q is a root of unity, which is related to the lacing number of G. So that's R is a lacing number. So it is 1 if G is simply laced, and 2 if G is of type B or C, and 3 for G2. And then now it relates to the representation theory of the Langlands dual Lie algebra. So affine algebra, so relates to UT G Langlands dual. So now it is a twisted affine Kac-Moody algebra when the lacing number is not equal to 1. So when I write relates to, in fact, more precisely, we obtain Poisson algebra, which is the Grothendieck ring of representation of finite-dimensional representation of the quantum group. So these are two limits, and in fact, there is a third one which is expected to be relevant. It is a Q=1 limit. So third limit, and it was not very much investigated. In fact, there are no general results about this limit, but it is expected to be interesting. Expected to be interesting for various reasons. So first, there are some examples where it's possible to compute this limit, and it seems to be related to representation of a certain simply laced algebra, I will explain. And also from the perspective of Drinfeld-Sokolov reduction, which was in fact one of the motivations to define this algebra, it's also expected to be relevant. So this is something which will play a role in this talk. So to which representation theory, how to understand this Q=1 limits. And so that's the first motivation. And the second motivation is from slightly different point of view. So it's related to Bethe Ansatz equation in quantum integrable models. So Bethe Ansatz equations. And in fact, more precisely, folded versions. So this is in the context of quantum integrable models. So which are certain equations which govern some roots of spectra of eigenvalues of relevance operators. I will explain later. And in fact, this folded version of Bethe Ansatz equations appear not directly in the context of quantum integrable models, but of in fact, differential systems which so appear or Murat-Obers can be seen as systems of differential equations. And so this folded Bethe Ansatz equation differ, they are not equal to the ordinary Bethe Ansatz equations related to quantum affine algebra or twisted or untwisted types. So are different Bethe Ansatz equations attached to quantum integrable systems attached to affine commutative algebra or untwisted, twisted or untwisted. And in fact, we may wonder if it's possible to construct quantum integrable models which will be governed by this set of equations. So construction corresponding quantum integrable model. So this is the second motivation for this project. And in fact, it's related to the first question, as I will explain. So to start with, I will give some more precise reminders about XXZ types model attached to an affine quantum groups. So reminders on quantum integrable models associated to UQG affine. So this is a XXZ type. So here we have Q non-zero complex number, and we assume that it is not a root of unity for this talk. Then we have so G hat, which is an in fact untwisted affine Kac-Moody algebra. Okay, so we in fact more precisely it is a central extension of the loop algebra G tensor with the ring of Laurent polynomial. And so we do not put derivation element here in the affine Kac-Moody algebra so that there are finite-dimensional modules. So then what is called, so we have a corresponding XXZ type. It lives on a finite-dimensional representation of the algebra. So let W be a finite. Okay, so usually W is called the space of states. If we want to use physics terminology, space of states. Then, thanks to the structure of the quantum group, in particular the existence of the R matrix, we can define a commuting family of operators, which behaves like a commuting family of Hamiltonians. So we have the standard R matrix construction, a commuting family of operators. Operators are usually called transfer matrices. So these are operators on W. And these operators depend also on a representation, which is another finite-dimensional representation of. So sometimes it is called to distinguish from W, the space of state, it is called an auxiliary space. And the parameter, which is so called the spectral parameter. So all these operators commute thanks to the Yang-Baxter equation satisfied by the universal R matrix of the quantum group. And in fact, it behaves well because it can be also written in an algebraic form, in the form of a morphism, so HW, from the Grothendieck ring of finite-dimensional representation of the quantum group to the endomorphism ring of W. So to V, we assign TV of Z. And here, this is a Grothendieck ring. So the quantum group is a Hopf algebra, so we can take tensor product of representation. And so we have the Grothendieck ring of ring structure on the Grothendieck group. Okay, so the study of the model is a study in particular on the eigenvalues of the operators, the transfer matrices of these commuting operators. And so, in fact, it's possible to extend, in fact, to attack this problem, to try to study the spectrum of the model, so the eigenvalues of these transfer matrices. It's possible to extend these transfer matrices to a more general category of representation. So this is something I had worked on with Jimbo and then with Frankel. In fact, so a way to state this is that HW extends. So let's say a map HW prime to a larger Grothendieck ring. We still go to endomorphism of W, and then we have also to add a twist parameter. So this, what is this hat prime? It's also a Grothendieck ring, but of representation not of the quantum affine algebra, but of a Borel algebra of the quantum affine algebra, so of a smaller algebra. So Grothendieck ring of representations of UQB hat is a Borel algebra. It is a Borel in the sense, the usual sense, in the sense of Chevalier generators. It is a Hopf subalgebra, and as it is smaller, in fact, there are more general representations, and in particular representation of the Borel algebra, for which the action cannot be extended to the quantum affine algebra. But still, the A-matrix construction works if we add certain twist parameter. So that it's a technical point, but it has to be added because we have to deal with infinite dimensional representation and take the trace on some infinite dimensional representations. That's why we have to add a parameter. So anyway, so why this is useful is because in particular, it allows to define new operators, which are called the Q operators. We have which are parameterized by a node of the Dynkin diagram of G. Q depends on Z and U, and they come in plus version of minus version. So these are defined as a transfer matrix as above, but of some representation Ri, which is a representation of the Borel algebra, but which is not a representation of the quantum affine algebra. So it is sometimes it's called the pre-fundamental representation. And then, so these operators have some remarkable properties, and let's state it in the form of a theorem that we have proved with Frankel in two papers published in 2015 and 2018. So the first point is that the eigenvalues of these operators are polynomials. So the eigenvalues of Qi plus U on W are polynomials up to a factor which is uniform, so which depends only on W. So up to what is called sometimes a universal factor that can be computed. Up to so they are polynomials, and so they have some roots. And the second point in the theorem is that these roots satisfy the Bethe Ansatz equation. So the roots, in fact, was conjectured by Frankel-Reshtitikin some time ago. So the roots of these polynomials sometimes are called Baxter polynomials. Forget about the terminology. So the roots of these polynomials satisfy Bethe Ansatz equations. So which is a system of algebraic relations between the roots of this polynomial. And in fact, we had proved it up to a genericity condition. And in fact, this genericity condition was then dropped by, in fact, it was removed. It's not necessary by Fagin. Okay, so this is a quick summary for the, let's say, the ordinary quantum integrable models attached to an untwisted quantum affine algebra. And so now I would like to discuss the new point of the project, which is the folded version of this. Okay, so what do we mean by folding? So it's related to in fact basic foldings of simply laced Lie algebra. So we pick up some G. So I will denote by G prime a simply laced Lie algebra. I take G prime to differentiate with the Lie algebra G. Let's say simply laced algebra, complex simple Lie algebra. And we assume that we have a non-trivial automorphism of G primes coming from symmetry of the diagram. And so that the sub-algebra of fixed point is G. It's well known that for G non-simply laced simple algebra, we can construct G in this form as a sub-algebra of a simply laced algebra. So that's a very well-known point of Lie theory. So now, so we have a corresponding picture in the quantum group side. So we have sigma automorphism of Q G prime affine. But now there is an important technical difference, is that the corresponding non-simply laced quantum affine algebra is not a sub-algebra of UQ G prime. So let's say, so that's a technical point, that UQ cannot see it as a sub-algebra of fixed points, as we did in the classical picture. So however, let's try to construct some corresponding quantum integrable models. So let's pick up W as we did previously, simple, so UQ G prime. And we would like, in some sense, to fold the picture, so to put sigma into this. So then there is a corresponding sigma for the representation itself if its highest weight is sigma invariant. So there is a corresponding sigma hat from W to W if let's say the highest weight, so the analog of highest weight in this theory, which are called sometimes Drinfeld polynomial, so of W is sigma invariant. And then on W we have also the Q operators coming from the simply laced types which act. So we have the QG as a box, Q operators from which acts on W, and we have we will also consider their semi-simple parts, so which will denote like this. So also acts on W. Okay, so now what appears? So our proposal of relevant space in this context is the following. So we'll consider a subspace of W generated by weight vectors, so W, so linearly generated by weight vector of weight which is invariant by sigma, so in P sigma, so that is to say it's a sigma invariant. So that so the Q operators have an action which is invariant by sigma. So that's a slightly technical definition, but so we assume that if we look at the action of QG and W, it's the same as if we apply the same operator, but with the node of the decaying diagram symmetric with respect to. So we consider this space. So the space of weight vector with sigma invariant weight, so that the action of the simply laced part of the Q operators is invariant on the point of the orbit relatively to the action of sigma. Okay, so that's a subspace of W, and we have the first few properties that I will state in the form of theorem, so theorem 2. The first point is that so the eigenvalues of this of the Q operators will give solution of the folded Bethe Ansatz equation in this space. So the zeros of the eigenvalues of the Q operators space, so they satisfy the Bethe Ansatz equation we wanted. So that satisfies the Bethe Ansatz equation. So that's the first point. And the second point is that we can be more precise, and this is where the W-algebra will play a role. So if we consider V be a finite dimensional representation of UQG prime, then then if we look at the corresponding transfer matrix, so it preserves this subspace, its eigenvalues can be written, can be obtained. So can be obtained, there is a more precise statement, if there are questions I can explain. So from a quantity which is obtained from a specialization of the W-algebra element. So what is called the folded Q character. So from the character, in fact, it is a Q equal 1 limit. So the third limit that I explained in my introduction of an element in this WQT algebra attached to G. So this is a theorem. So we obtain a space with a family of Q operators whose root satisfies the folded Bethe Ansatz equation. And in fact, so this is for the Q operator, but for the other transfer matrices corresponding to an arbitrary finite dimensional representation, we can describe the eigenvalues using some specialization of an element in the W-algebra. So that's first step, but it's not in this form a complete integrable models because we need the algebra of symmetry. That is to say, we need the Hopf algebra acting on this space. So to obtain completely a quantum integrable model, so we need an algebra of symmetry. So we need some action Hopf algebra, okay? Because if you recall how W of U is defined as a subspace of representation, but a priori there is no clear action, and it's not a submodule of W. So we expect there is some Hopf algebra, but we have to make it more precise. So that's the third part of my talk, and this is a conjectural part. So let's write in the form of a conjecture. So the first, before I state the conjecture, I would like first to remark that W of U, so if you remember the definition, it is generated by weight vectors, and the weight is supposed to be sigma invariant. So in fact, naturally, it is a vector space graded by invariant weights. So is vector space graded by invariant weights. So this is by definition. Okay, so now let's restate a conjecture that we have formulated. So we expect that the relevant Hopf algebra will be the Langlands quantum group. So let me be more precise. So for it is expected to hold for a generic U, for a generic twist parameter, a subspace in W, stable by the Q operators, okay, by the QG plus minus on the U, is isomorphic. So we expect also that it contains the highest weights. It's not the zero space. In fact, it contains the highest weight. Okay, so it is isomorphic as a graded space to UQ, so G hat Langlands dual module. We expect that inside this W of U, there is a graded subspace which has a structure of representation, but for the Langlands dual quantum group. First point of the conjecture, and in fact, it is more precise because we have precise information on this representation, which is again governed by the specialization of an element in this W-algebra. So more precisely, there is, so that's the second point of the conjecture, there is an element in this WQT of G, or its commutative analog. Maybe I can explain later. So there is a commutative analog of this W, which is called the ring of interpolating Qt characters. So that's a bit technical point. So these elements will interpolate between the two spaces. So at the Q equal 1 limit, we get the T character of the ambient space. And at the Q equal epsilon limit, we get the T character of this M of W. So this T character is a notion of character attached to the representation theory of this affine quantum group. And so this XQT will allow to compute the character of the representation inside M of W from the character of the ambient space. Okay, and so that's conjectural, but I will explain why we expect is true. And so this W of U, this is what this W bar of U, this is what we call the folded integrable model, because if all properties are satisfied, there is an action of quantum groups, which is U, Q, and G. So it's a bit intricated space because there is an action of UQ LG hat, but the structure is also governed by the Langlands dual quantum group UQG hat, and we have the Q operator, which are folding from the simply laced quantum affine algebra. So all these structures mix with roots whose roots satisfies the folded Bethe Ansatz equation. So why it is expected to be true? So what are the evidences? So first, it's possible to, there are many examples which can be described. And also we have a proof in the particular case of analogues of fundamental representation in this case. So we have a proof, so in our paper for the following situation, so for the particular case, when so U is supposed to be 0, so no twist parameter, and so when we have an analog fundamental representation. But by analog, why analog? Because if you remember, the highest weight of W should be invariant by the automorphism of the Dynkin diagram. And so in general, if we take a fundamental representation of the algebra, this property is not satisfied. And so sometimes we have to take tensor product of fundamental representation so that the highest weight is invariant by sigma, if the orbits has more than one element. So this is what I mean by analog. So it gives already a large class of situation where we can realize this picture, this W bar with an action of the Langlands dual quantum affine algebra and with the Q operator satisfying the folded Bethe Ansatz equation, and with the size, the character of the representation governed by a specific element in the deformed W-algebra. But in general, it's completely conjectural. So I would like to, so I think I have 45 minutes in total. So I would like to finish with some related problems and perspectives. So, so in fact, there is a bit surprisingly a combinatorial version of this picture related to crystal theory. So there is what is called the Nakajima monomial for crystals, monomial model. And in fact, so if we look at the combinatorial version of this picture, so this leads to the conjecture I mentioned, leads to a conjectural G crystal structure. So Q on the Q equal 1 limit of elements, so Qt that I have discussed previously in the fundamental case. So by fundamental case, as above, I mean when W is an analog of a fundamental representation. So there is this XQT, and we take the Q equal 1 limit. So we get something which looks like a Laurent polynomial, and the conjecture is that when we extract the different terms of the sum, then there is a G crystal structure which can be defined using the Nakajima monomial model for crystals. And again, this phenomenon can be observed in many cases by computation, but we have no idea at the moment of proof of this. Also, it looks quite elementary on examples, but I don't know how to prove it. So second point is that it's related to a recent work of Kashiwara and O. So there is a relation recent. So by recent, it's fact it's from I think the end of 2021 or early 22. So to recent work of Kashiwara O on rings. So what they call the rings of. So they studied these pictures so their motivation is slightly different. So it is motivated by limits of quantum Cartan matrices. So there are also deformation of Cartan matrices with two parameters, and they study also the Q equal one limit of this, and they consider some picture related to what is called the monoidal categorification of cluster algebras. So that's a slightly different framework. So anyway, so they obtain some ring which is seems to be isomorphic, in fact, to the rings of I explained previously. So corresponding to the Q equal one limit of this W Qt algebra. So I can also explain in more details if there are questions. And so first point I would like to mention is that we can take also the two limits simultaneously goes to one, when the two limits goes to one, so together, get a picture which is more classic and related to what is called the Godin model. And so in this case, the folding is a bit clearer because we do not get a new model, but we get a model attached to the Langlands dual of the simply of the finite-dimensional Lie algebra. So the folding has to the model, the Godin model associated to LG. So we do not get a new model as above. However, by investigating the folding procedure, it seems to give rise to a non-trivial embedding of tensor product of representation of LG to G prime. So however, there are some. So also in this case, which a priori seems more direct because we have the same model, we obtain some embedding of tensor product of representation. So gives morphisms from tensor product of simple LG modules. Okay, and so a last point I would like to mention that so there is also an open question, which is the definition of a quantum Casey equation in this case. So that's something we could not achieve, but we hope some maybe possible to do. So is there a folded version of quantum Casey equation in this context? So meaning a Casey equation which will reflect the structure of this model. So this is open problem. And okay, so I think I will stop here.
Moment. David will thank you again.
Thank you.